Yeah, so with this title, Prolegomena to Metaphysics of Black Holes, as you may have guessed, there is a reference to Immanuel Kant. There is this book, Prolegomena to any future metaphysics that will be able to present itself as a science, which was a bit unsatisfied with the reception of the critique of pure reason, so he tried to sell his philosophy with another shorter book. And the idea there is to build a science of metaphysics, or metaphysics as a science. But what I'm going to do today is more modest. I just want to talk about metaphysics of black holes. So it's more like a joke to use the word prolegomena. It's more a sign of the sketchy nature of my presentation and not a grandiose reference to Kant in a way. Also, something I want to say is that what I want to do is not to produce some kind of neat arguments for any claims. I just want to propose some kind of educated guesses, not trying to provide infallible truths about black holes, about their nature. So then you get a bit an idea of the kind of mood I am in with this presentation. Right, so here is the structure of the talk. I will first say a few words about the kind of questions I'm interested at. Then I will present a few physical theories and what they say about the nature of black holes. And then I will move to a more metaphysical section, trying to answer some of the questions I raised in the first place. All right. So here is one question I'm interested at. Are black holes objects or regions of space-time? Or are they both? Are they neither objects? They're not neither objects nor regions. Perhaps this question is a bit less obvious. Are there any implications for the nature of ontological categories coming from the nature of black holes? And the third question I'm interested at is, do they have any implications for the metaphysics of time? For this third question, I won't talk about it today because Sam will be presenting a joint work on that later today. So I will focus on the two first questions. Right, so regarding the kind of methodology I'm using, I think there is different ways we can go. Here is a modest path. You could try to look, try to find some results conditioned on a specific approach, like relativity, quantum field theory, but also some quantum gravity programs, which are not really theories. So I'm interested at different sorts of objects in a way. Well-confirmed empirical theories, but also more speculative quantum gravity approaches. A more ambitious path would be to try to find invariants in all approach to quantum gravity, to try to find some constraints on the way we are going to think about black holes by looking at, you look at all the theories we have, and you say, well, look, this feature is popping up everywhere in all the theories. So we have good reasons to think it's going to stick in the future, or that it's a real thing about black holes. So I think when you have this picture, it addresses to some extent the general worries that one may have, that we need a final theory of everything to do metaphysics of physics, or metaphysics of science in general. So for instance, Kerry Mackenzie had a couple of great papers going for this, that in a way naturalized metaphysics is in no better, not in a better situation than more a priori metaphysics, because it relies on some theories that we know are not fundamental. But I think there are ways to kind of, as long as you are not trying to find infallible truths, there are ways to address the worry by trying to find some properties that are in different places in physics. And by that I mean in different theories. Right, so today what I want to do is to look at three modest ways to clear the way for the ambitious one. So what I mean by that is that I want to look at something that general relativity says, but also semi-classical gravity and string theory. And it's just a start in the sense that if I'm right about the methodology of looking at all the series of quantum gravity that we have, we should look at all of them. But of course, it's super difficult. So here we'll focus on string theory. My impression is that what I'm going to say also works for loop quantum gravity, but I won't talk about it. right? So also you may ask, why am I just mentioned before fundamental theory, so why I'm talking about general relativity and semi-classical gravity that are not fundamental, usually not considered as fundamental theories, is because they are used as constraints on the development of theories of quantum gravity. So when you look at them, you get some kind of understanding of what is expected to stay in our future understanding of black holes and what might go, because you can build some kind of some problems, some paradoxes on the nature of black holes, with conflicting claims arising from different non-fundamental theories. We still trust in some domains of description. All right, so let's move to the black holes now. So you can meet those two guys here. As you probably know, the hole is a symbol of erudition, knowledge, and wisdom. But there are two holes in physics. One is general relativity, which provides an account of gravitation. The other is a standard model of particle physics, which gives an account of the quantum. But they don't work well together and respond to different philosophies. So what we do want is one theory, the theory of quantum gravity, which is able to describe phenomena that requires to have some understanding of the quantum and relativistic physics. So it's an oversimplification in a way. One could say there are three holes because there is also thermodynamics and statistical mechanics. But yeah, so the moral sticks. There is no unified picture of the physical world in physics. All right, so here is our first step on our way to theories of quantum gravity. It's general relativity. So black holes were a consequence of general relativity, at least in the contemporary accepted definition of black holes. And the idea is that when big enough stars burn up all the fuel, we have a formation of black holes because the nuclear reaction stops. So if the stars are big enough, they will collapse on themselves. And so those black holes in relativity are regions of space-time where nothing can escape, not even light. And it's a generic prediction of general relativity that there should be many black holes in the actual world. You have macroscopic black holes, supermassive black holes in the center of galaxies, perhaps primordial macroscopic black holes, perhaps also some kind of mass intermediate black holes at the center of global clusters. So they seem to be really real, at least in some sense, right? We have some objects or some phenomena in the world that are black holes. So in general, one important property is this idea of the event horizon, which is a border of the black hole, the region where nothing can escape, not even light. An important thing is that the space-time region is not special in GR in the sense that you can do some locally, if you do some physical measurements or things, you should not expect anything strange to happen there in the description given by GR. The second property is this idea of a singularity at the center, the idea that the space-time curvature and the mass density go to infinity. So it seems that physicists have different ways to react to those physical infinities. So they are problematic for many physicists. It's fine for other physicists. And also people think, okay, probably it might be just an artifact of GR not being quantum, that we have those infinities in the picture. And an interesting thing to say here, I think, that there is we should have a different epistemic attitude toward those two properties, in the sense that there are some doubts about the validity of GR at the center for the kind of reasons I mentioned, because we expect quantum effects to kick in. But usually people think we should trust GR for the event horizons, because we are talking of domains where quantum effects will not play a role. And the important things with event horizon, I mentioned this because Sam is going to talk about that later, is that the location of the event horizons are supposed to be global properties, right? So the idea there is not that black holes are like localized objects in space-time, but we should rather think of space-time as being space-time of a particular shape, singular space-times. that have a shape such as their region that we call black holes, something like that. The first thing I want to notice here that will play a role for what I'm going to say after is that we have this idea of a fungibility of matter fields into the metric field. I take this word fungibility from a paper from Nikogate and Keizo Matsubara, I will mention later, which in more metaphysical terms is the idea that objects can morph into space-time curvatures. It's like that, you throw some objects in a black hole and their energy is transferred from the matter field to the metric field, something like that. All right, so that's the kind of picture we get from general relativity. And now next stop on the way is semi-classical gravity, or also called quantum field theories in curved space-time. And that's the idea is to try to incorporate some of quantum field theory to general relativity, right? It's semi-classical because it's not a completely satisfying picture. It neglects the quantum back reaction of space-time on the matter field. So basically the connection between objects, quantum matter, and space-time is still a bit too classical. Would be one way to simplify things a bit. An important property here is a derivation of Hawking radiation, which means that the black holes are radiating away some of the mass. It's a very, for macroscopic black holes, it's a very weak radiation. So it's a very, very slow process, but still, it seems to mean that black hole are the kind of things that live and die. It's quite difficult to understand how this Hawking radiation works if we want a mechanistic explanation. But something quite important, which is frankly surprising, is that this radiation has a thermal profile, right? So, and what does it mean in physics that when a radiation has a particular profile, so it has a profile of a black body, and so it means that we can ascribe a temperature to the black hole. And it seems to be suggestive of a statistical underpinning of the black hole by micro degrees of freedom. So it goes against the no-hair theorem that we had in GR, where the idea was that black holes were kind of simple objects with just a few properties, a few global properties. But now, if that's really the case, that black holes have a temperature, it's highly suggestive that there is something interesting going on at the micro level. And it basically gives us reasons to consider that black holes are thermodynamical systems. So Katie is going to talk about that later. She will do, I mean, you will do a better job at explaining this. I will. But that's what we get from semi-classical gravity. To be honest, we already had, before semi-classical gravity, we could find some reasons to think of black holes as thermal objects, but it was not conclusive in the sense that it wasn't taking care of interactions between black holes, like fusions of black holes, something like that. All right, so the idea is that black holes are made of microstates, and it gives a view that's quite different from the view we got from GR. Because if black holes are thermal objects, thermodynamical objects, and we have this kind of idea that there should be a statistical understanding of entropy, it seems to mean that, yes, we have those micro states that could have many different states. Also, something quite interesting, I'm putting it here, how you're going to understand holography and where you want to put it, it's a bit complicated, but here what I want to say is that, interestingly, the entropy seems to be proportional to the two-dimensional event horizon surface, to the boundary of the black hole, and not to the three-dimensional bulk. So it's suggestive that the microstates are on the event horizon and not beyond it. But if that's the case, it seems to mean that the event horizon is not drama-free, so that when you get there, right in GR it says that nothing special happens, But now we have this kind of, we are wondering whether that's really true, right? Because it might be that the event horizon, there is drama, a lot of drama there, meaning like it's not a region which is just like other regions, something interesting must be happening at the event horizon. Right, so here I want to quote Curie and Bukilish from a previous version of the Stanford Encyclopedia of Philosophy. Here what I write, this is the idea that black holes are a converting device. When matter forms a black hole, it's transformed into a purely gravitational entity. When a black hole evaporates, space-time curvature is transformed into ordinary matter. Thus, black holes appear to be crucial for understanding of the relation between matter and space-time, and so provide an important arena for investigating the ontology of space-time, of material systems, and of the relations between them. Right. So in a way, that was a kind of talk that inspired me to think a bit about the metaphysics of black holes in the first place. That is a quote that is in the paper from Nick Huggett and Kaizo Matsubara, Lost Horizon, which is about the metaphysics of black holes in string theory. But anyway, already here, we have this idea already in GR, and it sticks in semi-classical gravity, right? So yeah, I want to ask you to keep in mind this property, right, of black holes, that they can change matter into space-time curvature. Okay, so I will not go through this to save a bit of time. Right, so now we want to move to quantum gravity. And so we are going to use the kind of result we have from the less fundamental theories to develop the theories of quantum gravity. What we want is to derive classical black hole metrics from the more fundamental ontology we get from a theory of quantum gravity, but also the laws of black hole thermodynamics. And by this I mean that those aims are guiding principles there are constraints used to try to build models in the framework of more fundamental theories. So now let's focus on string theory. As I said, for quantum gravity invariant, we should look at all theories of quantum gravity. But yeah, it's just a start. Okay, so in string theory, the black holes, the philosophy of black hole is quite different, because black holes are not anymore, it's not at all like in GR. In this case, you want to think of black holes as coherent states of strings. So it's basically the underlying strings and branes described by string theory can have different properties, and some of the states of those underlying objects, those strings, can generate some global states where you have a black hole. So now in string theory, it's like opening the Pandora box, because it's really, really complicated. You have many, many issues mingled. But I just want to remind you that there is this issue about the emergence of space and time in string theory, in the sense that it's too quick if you think that strings are just objects living in a 10 or 11 or 12 dimensional space-time. In fact, there are questions about the very existence of those 10, 11, or 12 dimensional space-times. The main reason for that is it's related to the problem of duality. So without getting into the details, the problem is that we have 5 superstring theories which are thought to be approximations or idealization, or at least to be related to a more fundamental theory. So those 5 superstring theories are 10-dimensional. Physicists think there is a more fundamental 11-dimensional theory, M theory, from which you could get those theories. And now very, very recently, people are working, so this is M theory, but many people now are working on something else called F theory, the idea being that type 2B superstring theory could be thought as an approximation of F theory. So you have questions about what is this network of different theories, and how do they track, I don't know, let's say ontological facts. So there is this huge debate about what does this all mean, that you have this duality relation between all the series? Because, okay, I didn't say what duality is. So the thing is that those series are very non-trivial, interesting relations connecting them. And what it means, basically, if you think of the series as spaces of models, you can draw a map between the models of the series, and that will lead to the same phenomenological physics as described by GL. So you could have, for example, if you think about T-duality, particular sort of duality, you can have different ways to compactify, let's call it the exotic dimensions that you have on top of the ordinary macroscopic dimensions. And you could compactify them in a very small way, a very big way, and you can show some mathematical results. Some of them are exact, that show that you can have theories with very different ontologies or models with very different ontologies that are underdetermined with respect to the description we get from relativistic physics. So in a way, you can rebuild a model of GR from different models of two string theories. And it seems to show that because those theories rely on very different spacetime, that those spacetime are kind of mathematical artifacts, so there is no spacetime at the fundamental level. And that's one very quick way, at least, to give you an idea about what's going on with the possible disappearance of spacetime in string theory. I want to say that because I'm not going to say a few things about something called the fuzzball model in string theory with a particular model to think about to try to represent a black hole with in the setting of string theory. But before doing that, I just want to read this quote from Joseph Polchinski. Finally, since we are thinking that space-time is emergent, we might try the slogan that it's not that the firewall appears, but that the interior space-time fails to emerge. But to claim this, we will need a better understanding of emergent space-time. Right? So the idea will be that if there is no space-time at the fundamental level, then you can have a picture where space-time emerge, but not all of it, like some parts of it emerge, and the black hole is it's a region that does not emerge, so to speak. Of course, now if I say this, it becomes quite, guys, what are you saying? That sounds a bit strange. So Nick and Kaiser are trying to flesh out a bit some possible ontological interpretations, what it could mean with this fuzzball model, that space-time fails to emerge at the places we think are black holes. There are black holes. Because just to be sure, the fuzzball model, sorry, I should have said a bit more about the fuzzball model. So with the fuzzball model, the idea is that you don't really have, wait, how did I, okay. Okay, let's just pretend you have event horizons with the fuzzball model. It's a bit more complicated, but one option is to think that there is no space below the event horizon, just string states. So you have the fundamental ontology of strings and branes. And you have, when there are some particular states, space-time emerge, but the black hole does not emerge, so to speak. Another interpretation is that there is no space and no string states either. So inside the event horizon, so there is no E-side at all. It's a category mistake to think that there is something below, beyond the event horizon. So we will have a genuine kind of, I don't know, ontological nothingness, something like that. That will be the end of being. Here I want to make an aside about, so Nick and Kaizo talk about, they suggest to talk about for reasons instead of event horizons. So for reasons, it's modeled on the French word faux, which means false. So the idea being that, in fact, what we are doing is replacing the concept of event horizon by another concept, which has some properties in common with event horizons, but which is different. And one is that there is a tension between one reason to replace the event horizon by 4 reasons is that the event horizons are global properties of space-time, which I mentioned before. When the idea with string theory and the fuzzball model is to try to have more local, a more local border of being, if you want, that does not require to be defined with respect to the whole space-time, to the whole cosmos. And it's super difficult. So I've been speaking with Mike Schneider about that, and he has a great draft on this topic that I recommend. And the way he thinks this, I think, is super interesting. He was saying, well, look, I was asking him, how do you think that the global feature of the event horizon is going to stick in the future with string theory and the fuzzball model? And because I was saying, well, look, I think my expectation is that yes, because we still need to recover at our scale the space-time metric. And he said, well, look, that's an interesting question, but from my point of view, it's more that there is a tension in the program from the start, that at the same time, they want to find a local underlying ontology of string and brains and recover as a semi-classical limit the space-time metric, which is global. And I think it's interesting. That's basically where my knowledge ends on this topic. I think it's interesting to see that, yeah, it's an open question what's going to happen with this global feature of the event horizon, whether it will stick or not. String theory puts some kind of pressure on that. All right, so just to conclude, just to mention, the Hawking evaporation is still present, or very similar at least. So that's not something that will disappear with string theory. All right, so now what should we do with all this content from physics when we move to metaphysics? Well, I want to go back to this idea of ontological categories. So here we are back to Kant. It's a table of the categories of Kant. So as you probably know, he's thinking that the categories are in the mind, in a way. Those are transcendental categories, conditions of possibility of experience. I'm not buying that, but just to give you an idea about what categories could be, I guess you ask any metaphysicians, they will have different views on the list of the most fundamental categories to think about the world. What I want to remind you of, thinking about ontological categories, is this idea of the fungibility of space-time and matter. Yeah, I forgot to say that one interesting evolution from GR and semi-classical gravity with respect to that is that with GR we had this idea that matter could be converted into space-time curvature, but with semi-classical gravity on top of that we have the idea that you can also do it in the other direction. You can move from space-time to matter with the emission of mostly massless particles, but also massive particles, I think. So it's one-way general relativity, two-way semi-classical gravity. Sorry. But of course, with string theory, things get a bit complicated because those conversions between those two categories of matter and space-time could be happening at a derivative level and not be fundamental. So it's something that we have also to talk about and to look at for building different classifications of what might be going on. Right. So the first question I asked at the beginning of the talk was about the category of black holes. What are those black holes? Well, I think it really depends on which theory you are looking at. If you look at GR, there are regions of space-time. If you look at quantum theories, there will be more like objects. But from a string theory perspective, in a way, I think we should say that there are neither objects nor regions fundamentally. It's more like they can be derivatively objects from the perspective of one particular theory, or space-time regions from the perspective of another theory. But when we move to the more fundamental theory, we have kind of, at least to string theory, you have some kind of evidence that black holes are neither objects nor space-time regions. I think it kind of speaks against this idea of fundamental object space-time separatism. That is, at the fundamental level, you can separate between material objects on the one hand and space-time regions. That is just a way to basically gloss over the fact that space-time may fail to be fundamental in a way. I think it kind of rule out standard relationism and substantivalism, at least at the fundamental level. And it's good for super substantivalism and super relationism. Not necessarily in a straightforward way, because you can super substantivalism and super relationism are still trying to defend the view that the cosmos, the whole cosmos, is either a fundamental space-time substance, and the impression of object comes from, or the emergence or the grounding of objects follows from the instantiation of some properties by the space-time substance. So that's super substantivalism. Or in the super relationist case, it's kind of the same story, but you replace the fundamental substance by a fundamental network of relations. But at the very least, you are not building from the start your views with this idea of a sharp separation between matters and space-time relations. Right. So back to the nature of categories. I will try to accelerate a bit. Let me just read this quote in blue. While objects can change the ordinary categories they belong to, what is a seed now might be a tree in 10 years' time, the membership in ontological categories marks one of their necessary features. That's a quote from Jan Westerhoff. And here is another quote from Lowe. An entity cannot undergo a change with respect to its own existence or identity conditions, and therefore cannot exchange its ontological category for another. So, I mean, there is a huge literature on the nature of categories, but what I want to take from that is that perhaps a standard view is that entities can change their ordinary category, but not the fundamental category. And I'm wondering, and I'm asking for your help really, whether black holes could be opening the way for a reflection on whether this is true, that entities cannot change their fundamental category. Because here is one question: are all entities entering and exiting black holes staying in the same ontological category? So I don't have the answer to this, but I do believe that the information loss problem and how we are going to address the problem may give us some kind of hints about how to think about the relation between the entities that enter the black holes and the entities that leave the black holes. And one way to go would be to say, well, look, the fungibility of space-time and matter suggests that space-time and object might be contingent categories. But it does not say yet, whether contingent categories are ordinary or fundamental categories. And I think there are two ways to go. So here is a possible way to try to argue that space, let's call it space-time, it could be space and time, that space-time is a fundamental category, material object also. So an argument could be like this, right? So you have this idea of categorical change, inbound, internal, and outbound entities experience category change. Those categories are fundamental, and thus individuals can change their fundamental category. So again, I don't think this argument is convincing. So for the first premise, it's basically some very complicated physics, how we are going to relate the inbound entities to the outbound entities, and how we are going to track them in the black hole. And so such an argument will have to rely on the possibility to produce such an identification. And regarding the second premise, at least in the framework of string theory or any theory of quantum gravity that make a claim that space and time are not fundamental, it seems that it rather shows that the space and time are not really fundamental categories. So we should not think that when you have kind of migration between those two categories, it's a migration between two fundamental categories. Sorry, there is no interesting violation of the idea in metaphysics that entities necessarily belong to their fundamental category. That will be one way to go. But now that if that's the right thing to say, then I think there is still an important implication, which is that we have no really access to the fundamental categories of the natural world. Because it means that categories as fundamental as space, time, or the idea of a material object are really emergent and are more akin to ordinary categories and to fundamental categories. Right, so to sum up, I think the fungibility of space-time and matter rules out many ontology of space-time, and that's a very interesting fact to note, to do some metaphysical work. The metaphysical nature of black holes, in my view, is really unknown. Fundamentally, they are objects and regions, but fundamentally, we don't know what they are. And maybe, depending on the auxiliary assumptions you are ready to make, maybe we could find some kind of idea that black holes put some pressure on the idea that entities always necessarily belong to their ontological category. I know it's a bold claim. I plan to do some more claims that, some more work in that direction with some colleagues to look at some concrete models of some quantum gravity models of black holes and see how we are going to try to identify some part of the radiation with the input entities. But yes, it's very speculative. I know that, of course. All right, so thank you very much for your time.